Hi, I'm going to tell you a little bit today about the calculations and the ideas and theories behind experiment 3 in Chem 102, solid and liquid densities. So let me tell you a little bit. Density is the ratio of mass of a sample to the volume of a sample. So to measure mass, we need to know both the mass and the volume. Because the mass and the volume increase in proportion to one another, if we double the mass of a sample, all things being equal, it also doubles the volume. Density doesn't depend on the size of the sample, so it's called an intensive property. This is in contrast to an extensive property, which both mass by itself and volume by itself are extensive properties. The interesting thing about intensive properties is because they don't depend on the kind of how much of a sample you have, they are helpful in being used to identify substances, or also in some other cases to determine purity. So the idea is that if I know, for example, the density of water is about 1 gram per milliliter near room temperature. It's not quite exactly that. We'll see how we can know it a little bit better in a couple slides. But if I go and make a measurement of an unknown liquid, and I find its density is 1.05 grams per milliliter, I can say this isn't water, or it's water that is somehow mixed with something else. So it's not pure water. And that's a really helpful property. There's a number of intensive properties used to do this. Melting point, boiling point, those are examples. So the idea is this is not an absolute proof. So, for example, if I have a substance that boils at 100 degrees Celsius at normal atmospheric pressure, I can't say for sure it's water, but water can't be excluded, and we can exclude all the other pure substances that do not boil at 100 degrees Celsius at normal atmospheric pressure. So intensive properties helpful in identifying things. As you can sort of see, if we want to determine the density of something, we got to make both a mass and a volume measurements. The mass measurements aren't too hard to make. We just take our object and put it on, or our sample, maybe put it in a container, put it on a balance, write down what the mass is. We do want to remember that oftentimes there's this container involved. So for liquids, we can't just pour the liquid onto the balance. We have to put it in a container. And so when we need to measure the mass of the empty container, measure the mass of the container plus the liquid, and then the difference between those two. And that's what I mean by measuring mass by difference. So we always want to remember that we need to isolate the mass of the sample when we're calculating density. So the first procedure in this experiment is measuring the density of a regular solid. And regularly shaped solids, so things that are kind of boxy shaped, where they have 3 straight edges, 3 sides that are all 90 degrees to one another. In that case, it's not too hard to measure volume, because we can use a ruler to measure the length of all 3 dimensions, and then the volume is just the product of those 3 dimensions. We're going to make measurements in centimeters, and that has the advantage that when we multiply 3 distances in centimeters together, the volume units will be centimeters cubed, and a centimeter cube and a milliliter are equal to each other. So whether somebody says grams per centimeters cubed, or sometimes let's say grams per cubic centimeter, or grams per milliliter, all 3 of those ways of saying units are actually equal to each other. So grams per centimeter cubed, grams per cubic centimeter, grams per milliliter, those all equal the same. Oh, I forgot to mention, we're going to be, with our mass measurements, we'll be using an analog balance, and those are just very precise measurements. They measure to essentially that's 0.1 milligrams or 1/10,000th of a gram. You'll notice in the videos that there's little doors on the sides of the balance, so you have to open a little door, put the sample on the pan where the mass is measured, and then close the door, and that's to account for air currents in the room that can serve to sort of, or they lead to less precise measurements or less accurate measurements of the mass, because the force of the wind is affecting the mass measured by the balance. So the first thing we're going to do is for the second and third parts of the experiment, we're going to measure the density of an irregular solid and of an unknown liquid, and we need to know the volume of a 25 milliliter flask. Oh, sorry, it says flash there. This is flask. So the density of the 25 milliliter that's printed on the side of the flask is not entirely accurate. I should say it's just an approximation, and we want a more accurate measurement of the volume. And the way we're going to do this is by using a liquid with a known density. And if we rearrange the density equation, we'll see that we can get this volume is equal to mass divided by density. So if we measure the mass using a balance and we know the density, we can find the volume. So we're going to get a more accurate measurement of the volume of this flask. And the liquid that we're going to use with the known density is water. There are tables that show the density of water at various temperatures, and we usually say water's density is 1 gram per milliliter, but we want a more precise measurement, and so we're going to measure the temperature of the water and then look up in a table the density. So near the end of your lab manual, there's a page that has a table with the density of water and how it changes with temperature. So this table is a little bit difficult to read, and therefore I want to talk to you about it. So the first thing is that every little cell in here tells the density at 0.1 degree centigrade Celsius intervals. And the way you read it is the rows indicate full degree changes in temperature, and then the columns indicate 1/10 of a degree changes in temperature. Now, the one thing you might notice is that except for 3 of the cells, they only have 3 numbers, but then there's these 3 special cells where we see they have 6 numbers. So what's going on there? So, like for example, up here we can see at 0.0 degrees it says the density is 0.999841. But then the next entry, and this would be at 0.1 degrees, it just says 847. What's going on is the table doesn't want to have to write out 0.999 for all these entries in here. And so what they do is just tell you the last 3 digits. And you have to realize that you need to look, and you always look up to I shouldn't say always, but usually you look up to the previous, to the cell above it in the table that has all 6 numbers, and that will tell you the first 3 values. So here we know that 0.999, that goes in front of all these numbers. Now, the one place it doesn't happen is every once in a while, the change from 0.999 to 0.998, it doesn't always occur right at the end of a row, and we can see that's the case here. So when we see that little asterisk in front of a entry, that means don't go back to these first three numbers. It means go forward to the next, the cell lower in the table with all six values. And you can see that we go from, the density is gradually decreasing, but then all of a sudden it goes from 007 to 991, and that's because we've rolled over the third 9, the 0.999. That last 9 has now become 0.998. We've changed that entry. So, for example, if we wanted to find the density of, maybe let's say I did 15.4 here, why don't we do 25 or 24.9? So if we want the density of 24.9, we go down to 24, and then we go over to 9.9, and that's this very last entry. And so it says 069. Now, we have to remember that there are 3 digits before that 069, and we go up, and the previous the last cell with all 6 digits above it is 0.997. So for 24.9, it's 0.997069. And I gave you another little example down here in case you're wondering. So the density of the irregular solid is kind of conceptually is the most complicated of the 3 densities. So for the density of the regular solid, we just measure the sides of the solid and calculate the volume. In the next slide, I'm going to talk about the density of unknown liquid. There, we just have to use the volume of the calibrated 25 milliliter flask. We'll fill it completely with the liquid that the unknown liquid we're working with. But here, our irregular solid, it can't be, because solids don't change their shape, we can't somehow make it completely fill the 25 milliliter flask that we've calibrated. So instead, what we're going to do is we're going to put the irregular solid in the flask and weigh it. And the difference between the empty flask and this flask with the irregular solid, that'll tell us the irregular solid's mass. And then we're going to add water to the irregular solid in the flask, and we're going to weigh it again. And then taking away that measurement from the mass of the irregular solid and the flask, we can find the mass of the water. And this is just water surrounding the irregular solid. It's not water that completely fills the flask, because some of the space inside the flask is taken up by the irregular solid. And therefore we can find the mass of the water and use the density from the value that we use to calibrate the flask. We're going to assume the water is the same temperature. We can calculate the volume of that water. Now, just like we can calculate masses by difference, we can calculate volumes by difference. And so we know the total volume of the flask. We subtract out the volume of the flask that's occupied water around the irregular solid, and the difference is the volume of the irregular solid. And you already know the mass, and therefore, you know the mass of the irregular solid, the volume of the irregular solid, you can calculate the density. The last measurement of density is density of an unknown liquid. So from the calibration, we know the volume of the flask. We're going to fill the flask completely with the unknown liquid and measure the mass. By difference, you get the mass of the liquid alone, and you can get the density. So that's sort of simple. In summary, density is a ratio of mass to volume. The mass measurements are easy, or relatively easy. The hard part is finding volumes. For a regular solid, it's pretty easy. We just use our ruler. For liquids, we can take a container, and as long as we can make sure that there's no air trapped in the container, we can fill it completely, and that will give a reproducible volume that we can calibrate based on a known density. We use the known density of water. And we found the volume of the regular solid by difference, and the volume of the unknown liquid is just the total volume of the flask. So that's a summary of what's going on in this experiment. If you have questions, let your lab instructor know. Have a good day.